In this video, we're going to take a look at example number 1 and example number 2. Now, I'm going to start here with example number 1 by asking you to see if you can pause the video almost immediately here to work through this question on your own. Can you use the definitions that we talked about in the last video to see if you're actually able to turn this improper integral here into a limit and then evaluate it? Go ahead, hit pause, see if you can work through it, and when you hit unpause, you'll see me working through the solution. Okay, so if I was working on this, one of the first things that I would do after rewriting my integral here is again to convert this immediately into my limit notation. I know this is going to look like limit of integral from 4 to not from 4 to infinity, from 4 to t, 1 over a root x dx. Keep in mind that the general thought process that we have here is that our curve, 1 over root x, which is going to look something kind of like this, maybe just starting at a value of 4, we want the total area under it. And so I can't find the area under it completely, at least directly, but I can find the area from 4 to t, and then I can just think about t sliding over. So I can go ahead and start to integrate now. Keep my limit notation here. Let's see, antiderivative of this, I think we could double check, but think this is just going to end up being 2 square root x, and I'm going to evaluate that from 4 to t. This is going to turn into a limit as t approaches infinity of 2 root t minus, I'm just going to simplify right down to 4, because I'm going to have square root 4 is 2, 2 times 2 right back to 4. Okay, so now that I have this, I just have to worry about evaluating that. As t goes off to infinity, 2 root t is going to become infinite. Minus 4, I'm going to get a final result of infinite. So my integral, which went from 4 to infinity of 1 over root x, is divergent. The area under it is infinite here. It goes on forever, and it's, extends endlessly far in this direction and produces an infinite amount of space. Now, this might seem very counterintuitive, because if you go back to the opening example that we had for this section, you'll see that we had a curve that almost looked near identical, but it had a finite amount of space. So there must be some meaningful difference between this curve and that other curve, which I think was 1 over x squared, which causes this to happen. Let's take a look now at example 2 and try to see the exact same thing in play. Again, I know that if I was to set this up as a limit, I would have to write this as a limit as t approaches infinity, integral from -1 to t of x times e to the x. I want to try to integrate this. Now this is back to a Calc 1 limit, Calc 1 integral. Well, actually I think this is a Calc 2 integral, because this is going to be a little bit difficult to integrate. Can you think of how I might be able to integrate this? Well, I think it's possible I could maybe do like an integration by parts. Okay, I'm even going to write this over here. Using integration by parts, oh wait a minute, I have a polynomial, and one of the pieces here, the e to the x, is easy to do antiderivatives of, so I'm actually going to set this up as tabular integration by parts. So let's see, I'm going to have my polynomial, and then my function that's easy for antiderivatives, and then my plus minus. All right, so let's see. I have x, 1, 0. I have e to the x, and all of its antiderivatives are e to the x. So let's see what we come up with here. I'm going to have a positive x times e to the x minus an e to the x. There's my antiderivative. So I'm going to have a limit t approaches infinity, x e to the x minus e to the x evaluated from -1 to t. Okay, so I'm going to have a limit t approaches infinity. See, I'm going to have t e to the t minus, oops, it looks like I lost a negative somewhere in here. Let's go back and quickly fix that. I should have a negative on this, which is going to change a little bit of what happens in here. My antiderivatives are going to be let me just rewrite that middle column there. But my antiderivatives here are actually going to look like, see, I'll have e to the negative x, then a negative e to the negative x, and then back to a positive e to the negative x. So when I put all of this together, my antiderivative is going to change slightly. I'm going to have a negative x, e to the negative x, and then a minus e to the negative x. That means that when I when I fill in this value of t, I'm going to see negative t, e to the negative t, minus e to the negative t. And then I'm going to have my negative 1 coming in, which is going to just give me 1 e to the 1 minus e to the 1. Notice that this back part over here is actually just then going to completely disappear, and I only have to deal with what I have at the front. I'm going to rewrite that a little bit more. I'm going to get rid of all my negative exponents here quickly by just rewriting these on the bottom of a fraction. Now, I think that the second term here is easy to evaluate because that limit is actually just going to turn into 0, right? Because e to the t is going to zoom off to infinity. So if I was to separate this into two limits, that second limit is going to be easy to work with. Again, I know that second limit just turns into 0. So really what I'm going to be left with here is a limit as t approaches infinity of negative t over e to the t. So what do I do with something like this? Notice that I can't just plug in infinity and get an answer, right? If I thought about where the numerator and denominator are going, the top's going towards negative infinity as t gets larger, and the bottom's going towards positive infinity. Wait a minute. This is a perfect time for some awesome Calc 1 limits, or limit ideas. What about using L'Hopital's rule? We'll see a lot here that in 3.7 the use of L'Hopital's rule can be very important because we'll be dealing with a lot of limit calculations where t is going off to infinity or negative infinity. And we'll oftentimes run into a scenario where we get something like an infinite over infinite. Remember that L'Hopital's rule said that you could have a limit that was going to produce the same answer as this. And the way you would find it is by just taking the derivative of the numerator and the denominator separately. So derivative of negative t is negative 1, derivative of e to the t is e to the t. This limit should have the same answer as the starting one. And of course, this has just answer 0. Wait a minute. So how much area is under this curve from negative 1 to infinity? 0? Wait, 0 area? How could there be 0 area under a curve like this? Well, keep in mind that typically when we have area that exists above the x-axis is considered positive, but area below the x-axis is considered negative. And so it must be the case here that I have some amount of positive area and some amount of negative area that cancel out. And if you were to type this function into the calculator and graph it, you'd be able to see those negative and positive pieces.